Good evening. Today we are going to see uh, welded plate girder, and in that we are interested with design of stiffener. Already problem of welded plate girder, so I can show you the problem which we have already solved in first video of welded plate girder, and for same video we are going to design the stiffeners. Now already if you will see the dimensions of this, that also I will show you. So we have dimensions provided, so you can see these dimensions, and then we can go to the stiffness. So we have 40 mm, that is our thickness of flange, then 12 mm thickness of web, then 600 mm we have width of plate, flange plate, and 1800 we have, that is width of, sorry, depth of web. So these are the dimensions, and then we have to actually go to direct step number 9, in which we are going to design the stiffener. So till this already we are in last video, and therefore I am directly going to design of stiffeners, and we are going to design stiffeners here, that is bearing stiffeners, that is transverse stiffener, in which we have bearing stiffeners and then we have vertical stiffeners. Generally we are not required to provide longitudinal stiffener, that is horizontal stiffeners, which is at point 2D, uh, D1 I can say, from face of the, from the compression flange. So we will not discuss in detail with this one. So we will go to design of bearing stiffener. If we will go to IS 800 2007, then you are going to see this. We have this 8.7.5, and that is we have design of stiffeners. And in this we have bearing check. You can see this. So fx on stiffener should not exceed the buckling resistance. So we have fxd of the stiffener as given in 8.7.1.5, where the stiffener also act as intermediate stiffener. It should be checked for the effect of combined load in accordance with 8.7.2.5. Now we have FPSD is equal to AQ FYQ upon zero point 0.8 gamma MO greater than or equal to Fx. And here they have mentioned Fx, that is equal to external load or a reaction. So now you can go this. So we have FPD SD or FPD is AQFYD zero point 0.8 gamma MO upon R. Now, if we will see our reaction value is 1110, so we will substitute that value. So we have 1110 into 10 raised to 3 into zero point 0.8 into 1.1 upon 250. That will gives me value of AQ as 3907.2 mm square. Now, outstand, that is given in clause number 8.7.1.2, where we have this outstand of web stiffener. Now you can see this, unless the outer edge is continuously stiffened, the outstand from the face of the web should not exceed 20 TQ epsilon. So epsilon we are generally taking it as 1. When the outstand of wave is between 14 TQ and 20 TQ, then the stiffener design should be on the basis of cross section with an outstanding of this one. So though your value is between 14 TQ to 20 TQ, you have to consider in design or in cross section as 14 TQ. So it is preferable you go to 14 TQ or less than this. So now we have assumed over here that is 10 TQ, that will be outstand, and then we are going to get area. So we have this outstand in this fashion. So 10 TQ, and generally when we will talk about end bearing stiffeners or load bearing stiffeners, we have these stiffeners as symmetrical stiffeners. So we are going to be in this fashion. So we have this as 10 TQ, and then we have this as TQ. Then similarly we have 10 TQ, and then we have this as TQ. And then from this we will get 2 times 10 TQ into TQ, and that will be 3907.2 mm square. And then by solving this, we are going to get value of TQ, that is equal to 14 millimeters. Now we have outstand at 10 TQ. So we can have this value that is equal to 10 into 14. So this outstand we can say 10 into 14. So we have this value as 140 millimeter, and this is symmetrical as end bearing stiffener. So we have this will be on both side of the web. So that is mentioned over here on both sides of the web. And when it is symmetrical with web, then we have to take moment of inertia about center of the web. Now we have to find strength of stiffener. It should be greater than the reaction. So that is given over here. Now this is the most important part, that is FQD should be based on the design compressive stress FCD C7.1.2.1. This is compression member. Already we have seen of a strut curve C. The radius of gyration being taken about the axis parallel to a web. So now this is again most important statement, parallel to web. The effective section is the full area of core area of the stiffener. Again see, total area of stiffener together with an effective length of wave on each side of the center line of the stiffener limited to 20 times wave thickness. Now, when we will go for reaction, so we are going to get this 20 TW on one side only. The design strength used should be the minimum value obtained for buckling about the web of the web or the stiffener. Now you can see this stiffener. We have symmetrical end bearing. We have for reaction. Then we have 10 TQ, 10 TQ, and this value we have calculated. We got this value, that is 14 is thickness, and 140 we have outstand of this stiffener. So we have these values. Then we have AQ. Now we have seen this 20 TW. This is my area of web into TW. Now, no, we do not have 20 TW on left side, so we have taken only on one side. If you have load bearing stiffener, that is load which is between the reactions, then we have 20 TW on both sides. Then AQ we will have 2 BQ TQ plus 20 TW into TW. And from this we will get, you can see this area of this 2 into 140 into 14 plus 20 into 12. So we have this value from center to this. So this value we are going to be as 240. That is 12 into 20 and into 12. And that area we will get as 6800 mm square. Then we have to find moment of inertia about center of the web, that is clearly mentioned. So we have to go center of the web to find value of r, because we have to find parallel to the axis of the web. And for finding r, we have we have, then we have to find I, and then we will get r is equal to I by a, because we have to find by using FCD, and FCD we can calculate by using KL upon r, and therefore R is required. And for this one, A is calculated, we have to calculate I. That is calculated. Now, first we have for this uh, bearing stiffener, so we have 2 into 2 times, because both side B D cube by 12. So we have this as B, then we have this as D cube by 12, which will be at center of this. Then we will get this distance till face of the web as 5 TQ, and then we will get it as plus again 2 times TQ into BQA into BQ plus TQ TW by 2 whole square. So we have BQ plus TW, and actually, so we have to take from center of this. So whole of this, and then we have square of this. This is value of H plus 1 by 12 TW into TW cube. So that is of this web. And then we will get this value. So this you can see we have 140 plus 6 into zero point 0.5. So we have actually h square, and h we have actually 5 tq plus tw by 2. So we have this value in this fashion, and we have square of this plus 1 by 12, 20 into 14, sorry, 20 into 12. This is thickness of web. So this is thickness of web, and that is 1 by 12 b. This is B, 20 into 12, this is B. Into D, we have this D. So 20 240 into 12 cube by 12, and this will gives me value of I. Now, knowing value of I, we can calculate R, which will be I by A, and that is 78.71 millimeter. Knowing this value, we have to take, you can see, the effective length of intermediate stiffener used in calculating the buckling resistance should be taken as zero point 0.7 times the length of the stiffener. That is depth of the stiffener. And we will take this value zero point 0.7 into 1800, because whatever depth of it we have same, hardly to 2 millimeter from both sides, so that we can neglect it, and that is to keep space between your flange and web, or to put it easily between the two, that length is taken as 2 less from top and bottom. Then lambda we will get it as 1260 divided by 78.71, which is 16. And then using table 9c, we are in position to calculate value of FCD, which is 225.2 Newton per mm square. And this value we will calculate strength, which is 1531.36 kilonewton, greater than reaction 1110 kilonewton. So this is end bearing stiffener, and you have to go same load bearing stiffener. So load bearing stiffeners we have not calculated in this. Then we have design of stiffener. So we have 8.7.2.4. Again, this is transfer stiffener, and end bearing stiffener also we have transfer stiffener. So d by c by d greater than or equal to root 2, we have I as 0.75 dtw cube, but our value is less than root 2, and therefore we have to go moment of inertia should be greater than 1.5 d cube t cube upon c square, and that we have substituted here, that we have d 1800 tw 12, and c we have provided 2200 square. So we have this as 3.12 into 10 raised to 6 millimeter to the power 4, and now we have to provide stiffeners which having moment of inertia greater than this. Now in this we are going to provide these stiffeners. So we can have this, if you will see, we have this vertical stiffeners. So second we have somewhere here, and this distance center to center we have provided alternately. So center to center between these stiffeners we are going to be as 2200 millimeters. 2200 millimeters. So now we have to take moment of inertia about phase when we have that is on one side of the web, and then we can have this value. So you can see this 2200 So tw into 10 tw cube by 12 plus tw into 10 tw. Here you can see we have taken 5 tw whole square, and that is equal to 3.12 into 10 raised to 6. Last bearing stiffener we have taken center, therefore we have to take tw by 2. Here we are taking phase, so we have just this value, that is 5 tw. And knowing this, we are in position to calculate value of tw, and that here we have considered tw, this is thickness of intermediate stiffener, or thickness of vertical stiffness. You can have both vertical stiffness. So this is not thickness of web. Here it is considered as thickness of stiffness. Or instead of TW, you can put it as TQ also. So you will not confused with this. So I can write it as TQ. And by using this, you are in position to calculate value of TQ. So we have this as TQ 20 TQ. Now you can see we have this on both sides, but are of no use because we are taking moment of inertia about face of the wave. And then we will have to provide 10 by 100 as intermediate stiffener. And then we have connection. So this is according to 8.7.2.6, that shear should not be less than tw square upon 5 bs. Bs is outstand, and we have taken this value, that is 100 millimeters. So you can see this tw square upon 5 bs, 5 into 100. So here actually they have taken tw, but if you will see tw, so they have mentioned tw as web thickness in millimeters. So we have it as 12 millimeter. So 12 square upon 5 into 100, we will get it as 0.29 kilonewton per millimeter, 290 newton per mm square. And then we have strength of the weld, that is equal to force, which already we have seen for connection between flange and web. So we will consider 6 because our thickness is 12 only, and weld length 100 Then we have this is as same way. So we have this tau r. So now this is my value of tau r, and then we have this as tau r, and we will go with this. So we have 410 upon root 3 1.25 zero point 0.7. So this should not be zero point 0.7 not 7. So this should be zero point 0.7 only, because we have from table 22. So we have this value as zero point 0.7 only, and by taking this value as zero point 0.7, we are going to get value of p, that is 277 millimeter. So now we will provide this pitch as 270 less than this center to center alternately, because we have taken this alternately. So we can see this. So we have this is 12 mm 1800, and we are going to provide this alternately, and that distance is 270 millimeter. So if we will see the clear spacing, we have maximum value as 200, and if we will go this, then we have 50 from this side, 50 from this side, 100. So this becomes your 170 millimeter, and this is less than 200 mm, less than 200 mm, therefore okay. So likewise we have to go for stiffners, and then we have to go for design of stiffners, and likewise we have to provide welds for these stiffners. So this is all about your stiffness and their connection with the plate. So today we will stop here only. So next time we will see the other part. Thank you.